Welcome to a journey through time, where we explore the fascinating evolution of science. From the ancient sands of Egypt to the bustling labs of the modern world, science has always been a beacon of knowledge and discovery. Let's start in ancient Egypt and Mesopotamia around 3000 BCE. These early civilizations made groundbreaking contributions to mathematics, astronomy, and medicine. The Egyptians developed a decimal-based number system and applied their knowledge of geometry to solve real-world problems like surveying flooded farmlands. They also created an official calendar with 12 months of 30 days each, plus 5 extra days at the end of the year, moving east to Mesopotamia. The Babylonians were equally impressive. They left behind records of star movements and developed mathematical methods for predicting celestial events. Their work laid the groundwork for future astronomical studies in the Hellenistic world, India, and beyond. As we move forward to the classical antiquity of Greece, natural philosophy began to take shape. Thinkers like Aristotle and Hippocrates sought natural explanations for phenomena. Steering away from mystical interpretations, however, with the fall of the Western Roman Empire, much of this knowledge was lost in Western Europe but preserved in the Byzantine Empire and the Islamic world during the Islamic Golden Age. The 10th to 13th centuries saw a revival in Western Europe, thanks to the translation of Greek and Arabic texts. This period of rediscovery set the stage for the scientific revolution in the 16th and 17th centuries. This was a time of monumental change as thinkers like Galileo and Newton introduced a new mechanistic view of the world. Supported by the scientific method, the 18th century brought the chemical revolution, where new quantitative methods transformed chemistry. The 19th century expanded our understanding of energy conservation, Earth's age, and evolution. By the 20th century, breakthroughs in genetics and physics led to new fields like molecular biology and particle physics. The post-World War II era ushered in big science, characterized by large-scale research projects often driven by industrial and military needs. Let's dive into the details of each century. Let's delve into the Middle Ages, a period often mischaracterized as a time of stagnation. In reality, it was a vibrant era of preservation and transmission of classical knowledge across 3 major civilizations: Byzantine, Arabic, and Latin. In the Byzantine Empire, the preservation of Greek heritage was paramount. After the fall of the Western Roman Empire, centers like Constantinople, Alexandria, and Antioch became beacons of knowledge. Scholars like Isidore of Miletus compiled Archimedes' works in the Archimedes palimpsest, while John Philoponus challenged Aristotelian physics and introduced the theory of impetus, a precursor to concepts in classical mechanics that later influenced Galileo. The fall of Constantinople in 1453 led many Greek scholars to flee to Italy, bringing with them classical knowledge that significantly contributed to the Renaissance. Meanwhile, the Islamic world experienced a golden age from the 8th to 14th centuries. This era was characterized by the thriving of commerce and the emergence of new ideas and technologies. Greek knowledge was slowly integrated into Islamic culture through translations of Greek texts into Arabic. Key centers of learning, known as madrasas, flourished. Education was personalized with certificates issued by individual teachers. Women participated as both students and teachers. Islamic scholars excelled in mathematics, refining and extending Greek and Indian contributions, such as the development of algebra and trigonometry. Significant advancements were made in astronomy and optics by scholars like al-Battani and Ibn al-Haytham. In medicine, Avicenna's The Canon of Medicine became a foundational text, and hospitals served as centers for treatment, teaching, and research. In Western Europe, the 11th century marked a resurgence of learning with the development of medieval universities starting in the 12th century. These institutions evolved from monastic and friar-led scholarly activities into independent urban centers of learning. Through the Reconquista and Crusades, Europe gained access to Greek and Arabic scientific texts, leading to a significant transfer of knowledge. Figures like Raymond of Toledo and Michael Scotus played key roles in translating these texts into Latin. Medieval universities emphasized the 7 liberal arts and later included higher faculties such as law, medicine, and theology. The works of Aristotle and other classical texts became central to education. European scholars and explorers, inspired by accounts like those of Marco Polo, sought direct routes to Asia, initiating the Age of Discovery. Advances were made in anatomy, metallurgy, and flight, contributing to a growing body of scientific knowledge. Join us next time as we continue our journey through the fascinating evolution of science. Now let's traverse the 19th century, a period that witnessed the birth of science as a distinct profession. In 1833, the term scientist was coined by William Whewell, replacing natural philosopher and marking the formalization of science as a separate field. Developments in physics were groundbreaking. Alessandro Volta demonstrated the first electrical cell to Napoleon in 1801, while pioneers like Giovanni Aldini, Michael Faraday, and Georg Ohm advanced the study of electricity and magnetism. Faraday, André-Marie Ampère, and James Clerk Maxwell unified these fields into the theory of electromagnetism, summarized in Maxwell's equations. Thermodynamics also emerged, bringing an understanding of heat and the concept of energy. Astronomy saw significant strides with the discovery of the first asteroid, 1 Ceres, in 1801 and Neptune in 1846. Mathematics grew with the maturation of complex numbers and analysis, thanks to Carl Weierstrass and others. Geometry and logic also experienced revolutionary breakthroughs. Electrical science led to technological advancements like electric power, telegraphy, the telephone, and radio. In chemistry, John Dalton's atomic theory in 1803 and Dmitri Mendeleev's periodic table in 1869 were monumental. Friedrich Wöhler's synthesis of urea opened the door to organic chemistry, leading to the creation of countless organic compounds. The exploitation of petrochemicals and the application of organic chemistry techniques to living organisms gave rise to biochemistry. Geology advanced with Charles Lyell, Adam Sedgwick, and Roderick Murchison's geological mapping and theories of mountain building, earthquakes, and volcanoes. The reality of ice ages and river valley formations over millions of years was established. Radioactivity and radiometric dating emerged, and Alfred Wegener's theory of continental drift, initially dismissed, was later validated by plate tectonics. Evolution and inheritance saw Charles Darwin and Alfred Wallace independently formulating the theory of evolution by natural selection, detailed in Darwin's The Origin of Species, 1859. Gregor Mendel's Principles of Inheritance, 1866, became the foundation of modern genetics. The germ theory of disease was proven by Louis Pasteur and others. Pasteur developed the rabies vaccine and made significant contributions to chemistry. Ignaz Fulop Semmelweis discovered hand washing to reduce puerperal fever, and Joseph Lister introduced principles of antisepsis. Economics saw the development of Marxian economics by Karl Marx, and the Austrian school, emphasizing entrepreneurship, replaced the labor theory of value with supply and demand. Psychology emerged as a science with Wilhelm Wundt's laboratory in 1879, followed by contributions from Hermann Ebbinghaus, Ivan Pavlov, William James, and Sigmund Freud. Sociology arose in response to modernization, with structuralism and rationalization as key concepts. Influential sociologists included Emile Durkheim, Max Weber, Georg Simmel, and Webb Du Bois. Auguste Comte's classification of sciences affirmed sociality as the basis of society. The Romantic movement opened new scientific pursuits, later replaced by positivism. Thinkers like Johann Gottfried Herder and Wilhelm Dilthey contributed to the concept of culture, and anthropology developed with distinctions between physical and cultural anthropology, influenced by Franz Boas. As we step into the 20th century, we witness an era that revolutionized our understanding of the universe and our place within it. This period saw the birth of some of the most profound scientific theories and technological advancements that continue to shape our lives today. The early 20th century brought about groundbreaking changes in physics with the development of quantum mechanics and the theory of relativity. Pioneers like Max Planck, Albert Einstein, and Niels Bohr introduced quantum theories explaining phenomena on a subatomic scale. Einstein's theory of general relativity, formulated in 1915, challenged Newtonian mechanics by showing that space-time itself could be warped by gravity. By 1925, Werner Heisenberg and Erwin Schrödinger had formalized quantum mechanics. However, general relativity and quantum mechanics remain incompatible, spurring ongoing efforts to unify them. In cosmology, Edwin Hubble's 1929 observation that galaxies recede faster the further they are from us led to the Big Bang theory, proposed by Georges Lemaitre. This theory was further supported by the discovery of cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1964, confirming the universe's expansion and helping estimate its age. The 20th century also saw the rise of big science, characterized by large-scale experiments and state-funded research, particularly in physics. Key developments included the discovery of nuclear fission by Otto Hahn and Fritz Strassmann in 1938, and the subsequent creation of the atomic bomb. Chien-Shiung Wu's work on uranium isotope separation was crucial for the Manhattan Project. Post-Wu, physics relied on massive machines and budgets to test theories, driven by both military and industrial applications. In genetics and molecular biology, the rediscovery of Mendel's laws in 1900 spurred genetic research. Linus Pauling applied quantum mechanics to chemistry, culminating in the physical modeling of DNA. In 1953, James Watson and Francis Crick unveiled the double helix structure of DNA, based on Rosalind Franklin's work. The Miller-Urey experiment in 1953 simulated early Earth conditions, demonstrating amino acid formation. Advances in genetic engineering and the Human Genome Project, launched in 1990, revolutionized biology. Space exploration took a giant leap forward with Cecilia Payne-Gaposchkin's 1925 finding that stars are mostly hydrogen and helium, initially dismissed but later confirmed. The 1987 observation of supernova SN 1987A and neutrino detection by Kamiokande marked milestones in neutrino astronomy, necessitating revisions in the standard model of particle physics. Neuroscience advanced significantly with Alan Lloyd Hodgkin and Andrew Huxley's 1952 model of action potentials and subsequent simplifications by Fitzhugh Nagumo. Bernard Katz's 1962 model of neurotransmission and Eric Kandel's research on learning and memory laid the groundwork for modern neuroscience, establishing it as a distinct discipline. Geology underwent a transformation with Alfred Wegener's 1912 continental drift hypothesis evolving into plate tectonics, transforming geology into a planetary science. Geophysics, meteorology, and oceanography merged, enhancing our understanding of Earth's dynamics. The 20th century also saw technological breakthroughs that revolutionized daily life. Electricity, the light bulb, the automobile, and the airplane became household staples. The radio, television, and computer transformed information dissemination. Advances in biology boosted food production and eradicated diseases like polio. The invention of the laser and optical amplifier facilitated the information age and the internet. Mobile phones, leveraging wireless technology, became primary internet access tools. In political science and economics, new theories and subdisciplines emerged. John Maynard Keynes's theories separated microeconomics from macroeconomics, emphasizing aggregate demand. Milton Friedman's monetarism and supply-side economics focused on money supply and tax reduction to spur growth. New classical and new Keynesian economics highlighted microeconomic foundations and market imperfections. Psychology transitioned from Freud's theories to behaviorism, led by John B. Watson and B. F. Skinner, and later to cognitive science. Advances in brain imaging spurred new research methods. Sociology, influenced by Talcott Parsons' structural functionalism, saw the rise of conflict theory and symbolic interactionism. Anthropology expanded its scope and refined methodologies, incorporating evolutionary biology into biological anthropology. As we move into the early 21st century, we see the validation and expansion of concepts that originated in 20th century physics. On July 4, 2012, physicists working at CERN's Large Hadron Collider made an astonishing announcement. They had discovered a new subatomic particle that greatly resembled the Higgs boson. This discovery was confirmed the following March, solidifying our understanding of how particles acquire mass. In another groundbreaking achievement, gravitational waves were first detected on September 14, 2015. This confirmed a key prediction of Albert Einstein's general theory of relativity, opening a new window to observe the universe. The completion of the Human Genome Project in 2003 marked a milestone in genetics, providing a comprehensive map of all human genes. This paved the way for advances in personalized medicine and genomics. A revolutionary gene editing technique known as CRISPR, developed in 2012, allowed scientists to precisely and easily modify DNA. This has led to the development of new medicines and holds promise for curing genetic disorders. In 2020, the invention of xenobots, a new class of living robotics, captivated the scientific community. These tiny biological machines made from frog cells demonstrated the potential for self-repair, and by the following year, reproductive capabilities were introduced. This innovation hints at future applications in medicine and environmental cleanup. The field of psychology also saw a shift with the emergence of positive psychology in 1998, founded by Martin Seligman. This branch focuses on the study of happiness, mental well-being, and positive human functioning, as a reaction to the 20th century's emphasis on mental illness and dysfunction. From confirming theoretical particles to pioneering new genetic technologies, the early 21st century is a testament to human ingenuity and our relentless quest for knowledge.